In current electricity topic, solving the circuits is very important at JEE level. For that, one need to know about the applications of Kirchhoff's laws. Let us now discuss in a detailed way how to apply Kirchhoff's laws in solving different circuits. In fact, we all know Kirchhoff's laws. The very first law is called law of currents. The statement is this: the algebraic sum of currents across any junction point in a circuit, that will be 0. What do you mean by algebraic sum? If you consider the currents which are incoming over there at that junction are positive, then the currents which are leaving the point are to be taken negative. Now in this particular case, sigma I is equal to 0. In other words, one can say the sum of incoming currents is equal to the sum of outgoing currents as such. So if I take a small example like this, there is a junction here, a part of the circuit we are taking up here. Now few currents are just entering and few currents are leaving the same point O. If I consider currents I1, I2, I3 and I4 are entering the circuit, that particular point O in a circuit, whereas I5 and I6 suppose are leaving, then the sum of incoming currents is equal to sum of outgoing ones. So how to write this equation? I1 plus I2 plus I3 plus I4. I am taking incoming currents as positive ones. Now minus I5 minus I6, that now becomes 0. That only we can rewrite it like this: I1 plus I2 plus I3 plus I4 is equal to I5 plus I6. In other words, you can just reiterate the same like this: sigma I is equal to 0. That in other words, we can say the algebraic sum of currents across any junction in any circuit, that will be 0. One theoretical importance of this equation is this: it is a direct application of law of conservation of charge. So theoretically, one should remember this is according to the law of conservation of charge. That is the importance to the first law of Kirchhoff. Now come to the second one, that is law of networks, we can call it. In other words, you can even call the same as law of EMFs. What is this statement once again? The algebraic sum of EMFs across a closed electrical network, that remains 0. The algebraic sum of EMFs across a closed electrical network, that must be 0. In other words, you can write the same equation as sigma IR is equal to 0. According to Ohm's law, V can be written as I into R, I being the current there, R being the resistance. So sigma IR is equal to 0. That is actually the statement we can give, or the equation for the statement of second law, that is law of EMFs or law of networks. Now while taking up this equation, how to consider the direction of current, that matters. In fact, we have a condition like a conventional sign for current is to be taken up. What is the convention we follow generally? When current is flowing in one direction in a circuit, when we are also taking the network in the same direction as that of the current in the circuit, then that current by convention will now be taken with a negative sign. If suppose we move against the direction of current, then we consider that current as positive. What is the reason for this? Whichever point we people are reaching in the circuit, about its potential, if you can understand, according to the potential of that point where you are reaching, we used to just give the convention over here. Suppose if you are going towards a point which is at lower potential than the other point, then you can say that current is to be taken with a negative sign. Suppose if you are going towards higher potential side, then that current is to be considered as positive. So this is one convention what we generally apply while taking up the second law of Kirchhoff. If I just give you a small circuit like this, let us consider here three resistances are now connected in parallel across a cell like this. This is a small circuit which all of you can directly understand easily. R1, R2 and R3 are three resistances which are now connected in parallel. Now the direction of current, of course, will be I here, that enters here. After reaching this junction, current now splits into three different parts. Let us consider the current across R1 as I1, the current across R2 as I2, the current across R3 as I3. So three different currents we are considering in such a way that the sum of all the three currents must now be equal to the total current that is entering into the circuit. So if you say at this junction current is split into three different branches, whereas at this particular junction once again all the three currents they reunite to give the total current as I. So what happens in this? The current that is coming out of the system, that again is going to be I only. That means I is the current entering into the system and I itself is the current which is leaving at the other end. That means the total current in that circuit will not vary. But individually, when you look at this resistance R1, the current across this resistor is I1, across the second resistor is I2, across the third resistor it is I3 as such. Now the question is, while applying this second law, let us name these points like A, B, C, D. This point I take it as E, this is F, this point as G and this point as H. Why we people are naming these points? One should understand first of all, to apply second law, what is a closed electrical network? When can we call that network as a closed one? What is the condition that is needed for that? Let us consider in this circuit A, B, C, D, A is said to be one closed network. That means what? You start from any point. If you can reach the same point without any obstruction in the middle, you can take that one for granted as if it is a closed network. For example, if you start from A, if you go to B, then to C, then to D and come back to A, this is a closed electrical network or a circuit. Such a type of closed networks, if you count in this circuit, you will be finding 6 by number. Look at these 6. A, B, C, D, A is one closed network. A, D, E, F, A, the second one. B, C, E, F, B, the third one. These are 3 internal circuits. Let us now check the external part of it also. If I take that AB, CD, GHA, this is one network. ADGHA, that is another network. Similarly, AF, ED, GHA, that is another network. So totally if you count them, around 6 closed networks we find in the circuit. You can take any circuit which is closed there, any individual network which is closed there, and you can apply second law of Kirchhoff for that. Let us now analyze that one. Let us analyze these networks now applying the second law of Kirchhoff, that is law of EMFs. Check the first network here. ABCDA is a closed network now. ABCDA. In this network, when I just move from A to B, I am just following the direction of current. In such case, current is to be taken with a negative sign. When I move from B to C, I am again following the current's direction. In such case, that current is to be taken with a negative sign. When I just move from C to D, in the same manner, current I1 is to be written with a negative sign. When we come back from D to A, I am just moving against the direction of current I2. In such cases, we used to take that current with a positive sign there. So here the current is negative, here current is negative, here also current should be taken negative, and here we can take positive. But in this regard, if you observe carefully, AB is that branch in which there is no mention of any resistance separately. Thereby, I into R, the product of I and R across AB can be taken 0. Exactly in the same manner, across CD also there is no mention of resistance. Therefore, the product of I and R will be 0 there also. So, no need for us to consider AB and CD because the product in each case as I and R is 0. Only thing we have to check is BC. So, how to write that product over here? It is minus I1 R1. In CD it is 0 plus I2 R2, that is equal to 0. It is nothing other than sigma IR is equal to 0. So, sigma IR means here I1 R1, here I2 R2. According to the convention, minus I1 R1, here plus I2 R2, that sum of course must be 0. Now, you can rewrite the same this way as I1 R1 is equal to I2 R2. This is actually the outcome what we can expect from the first network what we have considered. Likewise, let us analyze one more network here. This is ADEFA. I take ADEFA. This is the one which I am considering as a small network again. In AD, current is to be taken negative. In DE, current is there, but since no mention of resistance in that particular branch, IR will be 0. EF, when we are moving against the direction of current, I should be written with positive sign. Likewise, FA, the product of I and R will be 0. So, how to write in this particular network? Now you check it. Minus I2 R2 plus I3 R3 is equal to 0. So, what I can write now in this case? I2 R2 is equal to I3 R3. This is the outcome as far as second network whatever is considered here. ADEFA, that is the one. Look at the next one. Suppose if I take BC EFB, BC, EFB. Directly now you can write. In BC, it's minus I1 R1. In CE, value will be 0. Plus I3 R3 that you come across in this case EF is equal to 0. So what do you find once again here? I3 R3 is equal to I1 R1. Just look at the order carefully. Here I1 R1 is equal to I2 R2. Here I2 R2 is equal to I3 R3. Here I3 R3 is equal to I1 R1. So overall what we can understand from this, I1 R1, I2 R2 and I3 R3, all the three are equal. All the three are equal means, is it not individually equal to the value of voltage applied across? So we can say this is equal to V. So this is the outcome of solving all the three different networks which are closed by nature. Exactly in the same manner, let us just analyze at least one network from external circuit. Now AB, CD, GHA, let us analyze that network now. It is AB, I am taking up AB, CD, GHA. This network I take. If you see carefully, in AB, value of IR will be 0. In CD 0, in DG 0, in HA 0, only here we have to calculate and here we have to calculate. Only two values. So if you check in the first case, that is in BC, it will now be minus I1 R1. And of course, while moving from G to H, we are crossing the cell. While crossing the cell, you have to remember the convention this way. When you are crossing the cell from positive side to negative side, positive terminal to negative terminal, then you should consider that potential with a negative sign. If you are crossing from negative side to positive side, then we consider that potential to be positive. So if you check here, I am crossing between G and H, from G to H. That means I am crossing this cell from negative terminal to positive terminal. Therefore, automatically we should write that one as V, and this sum must be 0 according to that law. So what I can directly write from this one, I1 R1 is equal to V. That is the outcome as far as this closed circuit that is concerned. Exactly like that, if I take ADGHA, then you surely can understand I2 R2 will be equal to V. Similarly, if I take AFEDGHA, I will be finding I3 R3 is equal to V. So what ultimately you can get again? I1 R1 is equal to, I2 R2 is equal to, I3 R3 is equal to V. This is actually the outcome even if you analyze all the three possible external circuits. So what ultimately we have to remember as far as Kirchhoff's laws they are concerned. First and foremost, they are easy to apply and they will make your calculation much easier. You can analyze the entire circuit by parts. And second aspect, that first law is a direct application of law of conservation of charge, whereas the second law is the law of conservation of energy in this case. So Kirchhoff's second law is the direct repercussion of law of conservation of energy. And how to just take the conventional signs, if one is thorough with them, automatically you can solve and analyze any kind of a circuit, however big that is going to be. So this is the major application one should remember as far as Kirchhoff's laws they are concerned.